Thanks everyone for coming. Over the next half an hour, I'm going to talk about something I call CI/CD CS. Obviously, you know CI/CD, continuous integration, continuous delivery, but nowadays, especially at this conference, everything is continuous. So let's talk about continuous security. First, a little bit about myself. I'm Jorge. I work for a company called Sysdig. We do container monitoring and container security. No vendors page today. I do a bunch of things on GitHub, on Twitter, and I've been on the open source space for some time. I was involved in the Debian project. I've been doing things on monitoring, security. I love Internet of Things, home automation, home assistant. I also like cars. But let's talk about continuous security. But first of all, I'd like to do a quick intro into what is this CI, CD, and what leads us into CS. Let's start from the beginning. What is continuous integration? Let's put this in the context of Docker containers. So typically, if you want to do like the standard continuous integration workflow using containers, you develop your code, you push that into your code repository, GitHub, whatever it is. You have hopefully something that automatically triggers the build. Maybe you might have some multi-stage Docker files, so your final image is slightly smaller, and eventually that gets pushed into a Docker registry where you can pull from the images and start working. Okay, nothing new. What about continuous delivery, which is the next step? So we build the software and how we deliver the software. Actually, in the container world, in the Kubernetes world, we can make a distinction between continuous delivery and continuous deployment, which is a little bit more interesting. The idea is like we test the software, hopefully we deploy on a staging to do some additional tests, whatever, and then eventually the software gets moved into production. The difference is, do you do move into productions automatically, or is it a manual process? Ideally, we can do, or we should be doing that automatically, obviously depending on the environment, but if you want to do that with containers, with Kubernetes, there are a bunch of different tools that are going to help you to do that. I have mentioned a few, Helm, GitKeep, the ones I have tested myself, Scaffold, it's also quite popular. But we are not going to talk about continuous deployment today. That's a typical workflow of a continuous integration, continuous delivery using Kubernetes. This has been taken actually from the Google Container Engine documentation, where the developers, they push the code into a code repository. They have a software, Jenkins, whatever it is, that builds the software, gets pushed into a container registry, that gets deployed in a development environment. They do an additional testing of the software, and eventually, once that's validated, it's moved into a production environment. Nothing really different from what we are used to, just adopted Kubernetes as the infrastructure layer. But what about continuous security? What is this exactly? And probably the first thing we need to ask ourselves is, are containers secure? Do we need to do things differently? Adopting containers, adopting Docker maybe, Kubernetes, basically means a new infrastructure, or how we manage the infrastructure, new layers, and obviously new software, new layers brings new risks. But those risks, they are not going to be very different from what we have seen before. We have denial of service attacks, isolation breakouts, injections, SQL code, commands injection. And probably if we are already using Kubernetes, Docker, is because we have adopted all those agile DevOps techniques using that software, and we do that because we want to be very agile, we want to be very fast, and often security is just missed. We skip that because traditionally security has been, let's be slow, let's be conservative, let's have less moving pieces. But actually, adopting containers, it's an opportunity to do things better. It's not only new layers, new things we need to secure, it's an opportunity to do things in a better way. We have more layers, and security, it's basically an onion where we can build security at different layers that provides at the end increased security. And how we do security? Like generally speaking, basically, we like to isolate like different boundaries of privileges. Like development, it's like more relaxed. Production is more strict. We try to identify, minimize, and make those vectors where you can attack more smaller and more difficult to penetrate. We reduce scope and access. That's a typical example using microservices. One cool thing in microservices, we minimize the scope, the access of each microservice. We adopt new layers of protections and defense, like containers are smaller, less libraries, less processes doing just one thing. And hopefully we can add additional process for traceability or tests if we have all that process automated with CI/CD. But like DevOps and security teams, they are not usually best friends. DevOps people, they want to do things fast, be more agile. Security teams, they want to have less incidents. So they want to be slow, more conservative. There is this new movement that probably you have heard of, obviously buzzwords, which is DevSecOps. And it's kind of like similar story to this. Like before we had that separation between operations people and developers, why we need to have that separation or that fight or confrontation between DevOps and security. What if we could modify our processes to make security more agile? Try to deal with security as code, as probably you have done already with your infrastructure, with the way you deploy your applications. How can we react to a security event? Can we just open an issue, or we might decide to break the build in the same way we were treating the infrastructure? You deploy a new piece of infrastructure, if it doesn't work because you're using Terraform or whatever, which you just break that new deployment of infrastructure, or you create an issue. You can react in different ways, but all this, what it means is to treat security in a similar way to what you have done with operations, with infrastructure. And when trying to implement all these processes of DevSecOps, of continuous security, the idea is that we are going to do this at all the stages of the software lifecycle. Some people, they do it at build time. Some people, they do it at shipment, when you deploy the applications. But what happens after the application gets deployed in your production cluster? Do we stop security there? Do we just put encryption, firewalls, and we are happy with it? So let's see, as we go through all these different stages, how we can implement different security features: build, shipment, or deployment, and runtime. So as you're building software, your developers are building software, there are traditionally some techniques like analyze the software and search for specific vulnerabilities that they are well known. Licensing is another kind of like soft vulnerability that probably you want to look for when analyzing the software. Style, because obviously having your code look beautiful, it's also a good security practice. If you're using things like Git, GitHub, whatever it is, probably you can implement some policies of, okay, so master cannot be written directly. You need to do a branch, create a pull request, do some integrity checks on that branch, and once the pull request is ready to get merged, we do it, but not before. We can develop software using test-driven techniques, pretty much as you could be doing for unit tests. Or you can have the software and use some semi-automated scanning or security tests against your software. OWASP FAB scanning is a good example of software for doing that. And we do that as we write code. But once code is working, we are ready to build it, to put it in that specific container that will allow us to bring it into production. In our case, we are using containers, so let's leverage the opportunity that containers give us how to implement security. Number one, we should be using a trusted base image. We are not going to go to GitHub, say, hey, someone has built an image with Apache and PHP, let's use that. No, that's a terrible idea. You don't know how security updates are going into that image. You don't know who's maintaining that image. You cannot trust that. So you should define which are going to be your trusted base images in the same way you choose your base Linux distro. You're going to restrict functionality. So whatever it's the software that runs in the container, it should do just one thing and not multiple things. So don't install cron and supervisor the inside and have like multiple processes doing multiple things inside a container. Container is not a VM. It should do a single purpose thing. Let's try to restrict the number of libraries, dependencies we put inside. So don't put a monitoring agent inside. Don't put like backup libraries, whatever. Use multi-stage builds when it's possible. So the final image doesn't have any kind of like building tools inside. And restrict the privilege of that container. Don't run software as root. By default, when you create a Dockerfile image, almost everyone forgets to put the user option. Every software we run as a root inside a Docker container, eventually, if there is a container breakout, will be root. So treat a root user process in a container if it was a root user directly on your host. That's a very good recommendation. Control your privileged container, control your host access, host network, host process table, sensitive mounts. There are all these things that when we build the Docker file, when we build the manifests, we need to look at improving. But typically at build time, we are going to do one of the most popular security techniques when using containers, scanning the container images. That has become highly popular, basically because it's very easy to implement. We build an image, and then we have a software that just scans the Docker images or the container images and will let us know if there are any known vulnerability here. Okay, we are going to do an inventory, we'll have different priorities, maybe we can have like not critical vulnerabilities that we are okay with those containers moving into production. There are multiple software for doing that. CoreSclare, Anchor, a bunch of other open source and also commercial versions. And typically, like the way this software works, it's similar to this. This is the workflow for Claire. Basically, all these scanning softwares, they work the same way. They go into well-known vulnerabilities databases, like the Debian Security Tracker, Ubuntu, the Red Hat, CVEs, and they put all this knowledge into a database, and they scan inside the Docker image for software versions that they have these vulnerabilities. There are some other options or other products that they are more advanced, that they look for software which is not packaged. If it's using, I don't know, Python with pip or nodes, it can also scan those software installed outside of your packaging system. But more or less all of them, they work in the same way, using the package lists, the software installed manually, pip, rake. It's also very interesting to look for static binaries like Go. So someone builds a static single binary, how cool. But what about all the libraries included inside? We should look for that. Hashes of well-known vulnerabilities, and also lost credentials. Like what if a developer forgets and puts like a token inside the Docker image? Everyone with access to that image will have access to the credentials. Actually, this is how happened a hack into IBM Kubernetes clusters some time ago. And actually, this static scanning process can become very efficient because the way Docker container works. The way Docker images works is like you have your base image, and as you install software in it, or you create new images using the from option, basically it creates like a spanning tree of images. You start scanning from the bottom, and at the very moment you identify a vulnerability, you can already say that all the images that they have been built from that parent image, they are vulnerable. So this process actually can become very efficient. Once you know that an image is or has any vulnerability, the idea is our CI tool, it's constantly building all the images, and then this static scanning can go fetch the image, do the scanning, and push it into a registry. If there is this vulnerability, we will break the push. We won't push that into the registry. Some other people, or some softwares, it's possible to go into the registry and remove or forbid the image from being pulled. These are just different options, but this is the idea. We won't put the image available in the container registry. Many container registry tools, they already implement this out of the box. If you're paying for Docker Hub, Quay, or the registry options from all the different cloud vendors, they already include this because it's very straightforward. Okay, cool. So we have seen different things we can do at build time. Let's have a look at shipment. So one feature which is very, very interesting, and it's disabled at the moment, it's enable image signing. So you build an image of Docker. You can do it in your laptop. You upload it into a registry. Someone will download that image, will run it, but there is no full chain of custody of signing through the entire process. Someone could go into the registry, modify that image, and install malware inside. Or I could be a very bad developer, put something in the image, and I still have access, but I'm not trusted anymore by my company, and still being able to do that. There are different use cases. At the end, in the same way, this is a reality for Debian packages, for RPM packages. We should enable this for Docker images equally. So we want to have a signature that we can check, we can trust from the very moment we build the image until we pull and run that Docker image. Additionally, we shouldn't use just Docker Hub public repositories to upload our own software if that software is not public. Like you develop your applications and then say, oh, I'm going to have my developers to push this into Docker Hub. And then anyone can just download that software and do funny stuff with it. So if you have private software that shouldn't be public, have private repositories. Configure authentication, it's probably a good idea, and have all this workflow automated. Actually, you can also configure in Kubernetes what is called a validating admission webhook, so you can guarantee that developers that they can run images in Kubernetes, they are coming from a trusted registry, and they cannot just go into Docker Hub and run any untrusted software in your cluster. Actually, Google also has a project called Grapheas that actually allows us to track different policies and events at all these different points in your CI/CD CS pipeline. I won't get too much into the details of Grapheas. You can check it online, but it's definitely a good thing to do. And finally, well, first, this is probably common knowledge. The best practices that everyone has been talking for some time already on how should I implement Docker security, how should I implement all this in my CI/CD pipeline. But what about runtime? And this is what people are not doing very, very often. Basically, when we deploy an application, we still want to keep an eye on how those applications, they behave on our production clusters. So we need to look at what's happening at the host security, at the Docker engine security, and if we are using Kubernetes, at the Kubernetes security. specifically for the Kubernetes layer, there are a bunch of different projects, like the Kube bench that checks from standard recommendations of the Kubernetes layer. There is a similar project for Docker that checks for configuration and best practices at those layers. But what else we can do? Actually, Kubernetes provides a bunch of different security features that will help us to implement all this. First of all, it's airbag. This is basically permissions on Kubernetes. Kubernetes has namespaces that we could map those into applications or permission containers. And then we have different subjects that can be users or service accounts, which are the privileges that every container gets. There are resources, which are the other things inside Kubernetes that we can access, and we have roles and cluster roles. Those are basically actions that either a user or a service account can do. Can we list containers? Can we modify containers? Using role bindings and cluster role bindings, we can map or we can define what each user or what each container can do against my Kubernetes API. So, for example, if I want to deploy an application that it's going to check some internal behavior of my Kubernetes cluster, I will only give it get and list privileges, and I won't allow that application to modify everything. Or if I have a developer team, maybe I'm going to give them access into a specific namespace where they need to deploy their application and not into my entire cluster. Actually, this is an example of how you can define this configuration. The idea is that you create like some rules where you assign some verbs, like in this case, get, watch, list, that they can do over a resource, in this case a pod, and then I create like what it could be called like a group that's called read pods. It has only read access, and I put a number of subjects, which in this case are users, into that specific group. This is more or less how these permissions work in Kubernetes. But there are also some other cool things we can do. That's called admission controllers. Admission controllers in Kubernetes basically means that we have like a way to intercept how we instrument, how we instruct Kubernetes to create, manage a given resource, typically a pod. We have deny, so we have 4 examples of different admission controllers that we can use. First one, deny escalating execution, basically that allows us to forbid that given container can execute commands in privileged node. Node restriction doesn't allow the kubelet component, which is the one that creates the different containers, to access containers or how instrumenting containers in a different node in my cluster. So if one node gets a security incident, won't be easy to spread into other places. Validating admission webhooks, we have seen an example before, and what's really, really interesting is pod security policy. That's going to allow us to define that if a specific pod and a specific resource doesn't have a minimum security configuration that we have defined, the users won't allow, or the Kubernetes won't allow users to run those pods, those containers. What's going on here? Hello. Okay, there we go. So things that you can do with pod security policy. So you can prevent creating privileged containers or containers that they have access to third-party resources on the host. You can prevent users to run containers that they don't run under a non-privileged user. Prevent users to run containers that mount sensitive host paths inside the container, or that they have capabilities, which is like a way in Linux and in containers to crypt different resource privileges to have more permissions that the container should. We can also be like more strict and say, hey, if you don't have an AppArmor or a SecCom profile defined for this specific container, I won't allow to run the container. Another very simple to do, a very simple thing to do, and some people miss, is resource management. Like, let's set some limits on what are the resources that each container can do. Typically, nowadays, if your application is going to be hacked, most of the times, hackers are not going to try to steal credentials or install things. They are going to run basically cryptocurrency mining. So if you set up resource management limits, those incidents, they don't have such a big impact, okay? So in this case, it's memory, but it's also available for CPU. Basically, all the resources that they are namespace in a container, we can set up some request and limits. Request is the minimum you need, and limit is the maximum you get. You can set up network policies, very interesting. This is like the firewalling in Kubernetes. There are a few different layers for doing that, Cilium, Calico. By default, Kubernetes uses IP tables, but if you have a very complex setup, won't scale for you. There is an audit system for Kubernetes that you should be auditing, obviously. And come on, like nowadays, deploying TLS everywhere should be easy. Like we have ingress controllers, we have Let's Encrypt, like certificates, they are everywhere in Kubernetes. All the different pieces, they can authenticate and they can encrypt the communication. So don't miss the opportunity to do that. But we can do more. We can look at how the applications, they are behaving. We can detect if our application is trying to scale privilege. We can detect if the network is doing different things that it shouldn't be doing. We should look at what happens after there is a security incident, and we can do postmortem and forensics. We'll talk more about that later. Typically, an attack, it's going to be multiple steps. It's not like just one thing. No, they are going to probably like hack an authentication system, then probably they will try to get like remote access, like using a reverse shell or command injection or something like that. And then they will install some malware, and then we'll try to steal some sensitive information or run crypto mining software. At the end, any successful attack means that there is a small step that we haven't been able to block. And we are not being able to block it is because we don't know it. So what if we could look for what is called indicators of compromise, things that it could be a potential attack. We don't know for sure, but a combination of those gives us more confidence that that's an attack. There are a few different techniques for looking at runtime. When it's seccomp, basically allows to get a process, a container in what's called a sandbox and restrict the number of syscalls you can execute in that container. It's a very cool idea, but it's very limited because some things it's obvious that we are going to block, like reboot the host. We should never do that from a container. But it's not the same thing to allow a write into I don't know, like a credentials file or a read in a credentials file, the reading on etc result.conf. One should be fine, the other it's more sensitive. So it has very little context. We cannot define where a system call is fine and where it's not. There are more advanced software like Linux or Paramore that they have all these high-level resources like files, IP addresses, ports, processes. They are way more complex. They have way more features, but they have very little knowledge of what's a container, what's a namespace, what's a Kubernetes resource like a namespace, deployment pod. So this is one of the reasons why we decided to create Falco. Falco is an open source software that basically allows to detect any suspicious activity defined by a set of rules. It's open source. It uses the Sysdig filtering expression, which is very, very similar to TCP/DOM. And we have converted that into a YAML language that also defines those process behavior and understands containers and orchestration tools. A few examples have to do that. So what if someone runs a shell into a container? It's the first example. Well, if the container ID is not the host and the process name is bash, let's trigger an alert because someone has done docker exec bin bash and has started to hotfix things in a container in production that it should be doing. Last one, a process tries to access a camera. That's more a desktop example, but that's very cool. If there is someone opening this device in /dev/video serial, and the process is not either Skype or WebEx, there is someone trying to spy us through our webcam. So let's trigger an alert. Creating these alerts, it follows these syntax. For example, here we are detecting if a process has been running more than 5 seconds and it starts reading again the Kubernetes secrets that it has mounted. That doesn't have any sense. Typically, when you run software in a pod, you read all the credentials you need at the beginning. If that process in its life starts reading again those credentials, it's probably because you have been hacked and someone is modifying the behavior of that container to read again those credentials. Obviously, this depends on your application. That's why you are writing your own rules, but it's an example of it. But we want to do even more. With all this knowledge that we have of how our applications work, of all the security steps we have implemented, we should close the gap and do incident response. What happened when we have been hacked? What happened? Where that happened? Who did it? Why? We can have logs, but everything that has not been instrumented to log information basically won't exist. Can we SSH into production servers and start messing around, installing forensic tools in your production clusters? That's probably a bad idea. If you maybe those have a performance impact, maybe you affect production, but what if the container doesn't exist anymore because Kubernetes has killed it? Basically, you have zero information to do forensic and postmortem analysis. In the past, when you had to do forensics, when you had to do very deep level troubleshooting, we used to use Wireshark because it allowed us to go very deep, very into details of connections. What if we could do the same thing, but for the entire system? That's exactly what Sysdig, the troubleshooting tool, is about. We capture all the system calls, we put them into a ring buffer, and then there is a user space process that collects all the system calls and brings Kubernetes, Docker, Mesos metadata, so you have the best of both worlds, of the low level, all the information, the source of truth, which is the system calls, and all the high level service view, which is inside your orchestration software. And how we can use that information for doing forensics. Come on, system calls, that's something not everyone understands. How my developers, how my operations people are going to use system calls? Well, the reality is that if we look for specific indicators, we are going to know a bunch of things. So for example, if we see a clone or execve system call, that's going to mean that someone has created a new process, has run a command on my system, on that specific container. If someone is doing open or close on a specific file descriptor, that's someone either reading or writing into a file. If we see a socket connect, except there is some kind of network activity. So let's try to use that low-level knowledge to understand what was happening. But you will say, hey, this is super low level. That's going to be very, very difficult. What if we have a way to analyze system calls from a higher perspective? So we created this other software, which is also open source, Sysdig Inspect, that's going to allow us to map high-level activities like file activity, network activity, security events, or performance indicators, even logs, into the specific system calls. In this screenshot, there is 1.2 million system calls. And we are going to be able to browse through all these things and see basically how it works. So before doing a very quick demo, because I still have 10 more minutes, just a quick recap. So we have seen different things we could do at build time, different things we could do at shipment or deployment, different things we can do at runtime, not only security features that they are available at the Kubernetes layer, but also configuring SACOM, configuring maybe Falco, looking at what the application are doing inside the containers, okay? Finally, we couldn't close this continuous circle without forensics, because if we have a security incident and then Kubernetes kills the container, probably the only thing which is left is going to be logs and metrics, and it's very little things that we are going to be able to do with that. So now let me switch into my desktop and let me open inspect. So this is the UI of Sysdig Inspect. And now I'm going to open one of the capture files that I have here. Let me find it. Open source forensics. There we go. So this is a capture that I took into an application. This was a simple internal application that allowed me to ping different machines on my network. I had to log in into that specific application, and once I was there, I had like a form that allowed me to ping different hosts inside. It's stupid, simple, but enough for demo purposes. So I have seen that I have different requests going through my application. And actually, if I click here, down into this timeline, I can see how different users, they were making requests. I can go and analyze a specific request. And I can isolate the specific request. So I can see how there was a get, and then there was the post, and then it was the get of this specific component. I can see actually the form and the reply. But if I look at the output, I see something suspicious, like some process that it shouldn't be there. How come like a PS output could be happening on inside an HTTP request? I can go and see the executed commands, and I see how it's getting correlated. So every time there is a request, there are a number of executed commands. Let's see for these specific requests, which were the executed commands. So I see the ping, but also I see how someone ran PS, and also someone ran ls under another directory. I can see something here really, really suspicious. Someone is somehow injecting commands into my firm. How can this be remotely possible? I can go into my application activity and decode the entire network communication. So containers, this has changed. Oh, hold on. I just did install the new version of it. Probably there is an issue. My streams. There we go. Okay. So let me zoom back into that specific request I was analyzing. And I can see already how form data name, but then there is password, and the value, the date on the password, there is some kind of SQL injection. So I can see how someone is sending me data and work around in the validation of the form. But also looking at the IP address field, I can see how they are also injecting the command. So I've been able to understand that they are doing an SQL injection to bypass the authentication, and then they are doing a command injection to execute code on my server. There are other things I can do. Okay, I've been hacked. Let me see which have been all the executed commands on my server. And now I can see how they run a PS, ls, how they saw the source code of my application, and then how they downloaded what it seems to be a rootkit and de-executed it. So let me look at the specific content of those requests at the end. I'm going to see how they downloaded this, but then eventually let me see, hold on, this has been changed. How once they could download the rootkit, that rootkit basically could dump my entire database and see all the sensitive information of my database. All this, it's being stored in a file, and I have all of the information to do the troubleshooting, even if the container doesn't exist anymore. So that's going to be a cool thing to close that gap and being able to implement security across the entire thing. So that's everything I have for you today. I hope you have some questions, because I have 4 minutes more. Thank you. I think we have one here.
Doesn't the overhead of that Sysdig get really big if it's logging all the input and output of every file and
yeah, it can be resource intensive, but the idea is we are not going to record all the system activity all the time. That will be a nightmare to do. We will do it when we have one of those indicators of compromise. So typically attacks on containers, they are automated. So just recording a few seconds, it's going to give us enough information to understand how we were hacked and what they did after.
I also would like to continue the topic of the consuming of resources which you should spend monitoring and using your tool like Sysdig Inspector. Let's imagine that we have a Kubernetes cluster, and you mentioned during your presentation that you're monitoring some processing running inside containers. What if you have just thousands of pods, and how are you going to monitor network? Okay, network activity you could scan, but again, it's network activity in the dedicated, isolated subnetworks in the Kubernetes cluster. Then you should monitor processes inside container. Mm-hmm. And if you monitor not only one container and the whole cluster, how it's possible and how it is resourceful?
Yeah. Very interesting question. The idea for doing that is leveraging Kubernetes knowledge. So when you deploy an application inside Kubernetes, we could assume that a deployment is getting mapped into a microservice, because a deployment basically manages images of the same type. So we could say, when deployment is ready, let's apply this specific policy. And the policy can say the only allowed process in this container is Redis server and nothing else. If it's Nginx, we could say when the deployment name is Nginx, or when container image is Nginx, the policy I'm going to apply is the only allowed process is going to be Nginx. But not only processes, we can detect like network activity, processes listening, files that they can be read, but also paths where you can write. So you can define all those policies on specific images or on specific pods, and then leverage Kubernetes metadata to apply those policies to the specific pods that they should match, even if they change from the node, whatever it is. That's very dynamic, and it's very useful to use Kubernetes metadata for that. No other questions? Well, thank you very much. I have a plane to get, so I'll rush to the airport. Thank you.